Nos enfrentamos
In
ahora,
this lesson, we face a very interesting example. I can tell you that I've developed this example during 20 years in the classes that I've taught with these methods of linear algebra, which are somewhat revolutionary. My students have loved them enthusiastically. I hope you also get excited and you become motivated to continue working with these so original methods. The problem we deal with is the one illustrated in the figure. It's a problem of a water supply network. Notice that we have two deposits that supply water to a city. In this case, they are two deposits and we have a pipe network to distribute the water to certain consumption points. Notice that in the consumption points, we have outwards arrows, which means that we are there extracting water from the system, and where there are deposits, the arrows point inwards, that is, there we are introducing water to the network. So, the issue is to design that network of pipes, and find all the possible ways to carry to each to the consumption points the flow amount they need. A very important thing with which you usually have some difficulty when raising problems, is that before using mathematical methods and write equations, you have to study the problem and be clear about what you want to solve. For example, one of the things we have to clarify is what are the unknowns of our problem and what are the equations. Even though this might seem trivial, it is not so trivial and people have difficulties. Sometimes we do not know very well what to do. If we want to know how to distribute the water, of all possible forms, from deposits to consumption points, we have to know what the equations to be used are, and which are the unknowns. This is the first step you must consider. On the other hand, you also have to know what the data are and what the unknowns are. Sometimes, we do not know very well what data are and what the unknowns are. In this case, it seems logical to consider as data the flow amounts to be consumed at each of the consumption nodes. What flow do we need in each node, that is, the amount of water required at each consumption node and how much flow enters to the network from both deposits. In principle, they do not have to be equal amounts and can be completely different, and, in fact, they will actually be different. This is the first step. Next, you have to see what the unknowns are. Here the data seem clear. But, what are the unknowns? We can think that the unknowns are the flow amounts that circulate through each of the pipes, because we want to know what flow must circulate by each of the pipes, to be able to send water from the tanks to the consumption points. Then, we number all pipes, 1, 2, 3, etc., and we put an unknown in each one, with which the number of unknowns will be equal to the number of pipes. It is convenient to put an arrow to each flow, to know in which direction the flow is, initially, assumed to circulate. We do not know in advance if the flow is going in one direction or in the contrary direction, because, as there can be many solutions, there may be solutions that have the circulating flow in a given direction and others, in the contrary one, but we put any one, and, if at the end the direction is the reverse one, what will happen is that the corresponding unknown will take a negative value, instead of a positive one. If it is positive, it means that the flow direction coincides with the initially selected arrow, otherwise, it will be negative, that is, the flow circulates in the contrary direction. So, do not worry about the direction of the arrows. Normally, if we are close to a deposit, the flows would exit the deposit, and if we are close to consumption nodes, an important part of the flow will have the arrow towards that node, but it should not be a cause of concern. Then, we already know the number of unknowns and now, the question is, what are the equations? How many equations do we have? And what are they? The equations are simply the flow balance at each node, that is, the amount of water that enters plus the amount of water that leaves the node has to add 0, because otherwise, we would be generating artificially water, where there is not. Since in this case we have 2, 4, 6, 8, 10, 12 nodes, you count them and we find that we have 12 equations. It is important to note that the node numbering is important. Even though it may seem that from a mathematical point of view it makes no difference, from a practical point of view it really matters. So, what the equations represent is that the sum of all the flows that enter and leave each node is equal to 0. Since we already have the arrow directions, we know which ones come in, and we know which ones come out the nodes. We add everything and we must get 0. This can be done in matrix form, as you have there. In that column matrix, we put the unknowns that go from x1 to x15, and then at the end, we write a column matrix on the independent terms, which represent the flows that come from the deposits and the flows that we take for consumption. Then, we get a system in matrix form. If we develop that, we get a system of 12 equations with 15 unknowns, which is a linear system of equations. This is the system to be solved. If we number nodes inadequately, for example, if we number them as indicated there, not matching the previous numbering, the matrix, instead of being a matrix with a narrow band, becomes a scattered matrix. This has inconveniences, because when it comes to store it on a computer, it's more difficult to store. Everything that is 0 need not be stored, so that we store only entries which are different from 0, and if there are many non-zero blocks, they are much harder to store and cost much more. Then it is important that you get used to, in this kind of problems, to take care of the node numbering, because it has a practical importance. So, we have a system of equations in matrix form, that is, a linear system of equations, that is, equalities. This is what appears there, nothing more. So, we can ask ourselves, first, if it has a solution and if the solution is unique. The question of whether or not you have a solution is the compatibility problem, that we've studied previously. How do we study the compatibility of linear systems? If we apply our method, what comes out is that the sum of all the flows that enter and exit to and from outside the network has to be 0. This is what we expected. So, if we fix the amounts of water leaving the deposits, they must match the total amount we take out from consumption points. Of course, assuming there are no losses, this is our compatibility condition. If the entering amounts of water are larger than the exiting ones, the system has no solution and cannot be solved. The same occurs if the exiting amounts of water are larger than the entering ones. So, the amount of water that enters and exits the system has to match, which is equivalent to adding everything, with the corresponding signs and forcing it to be 0, that is, the condition that you have there, adds from 1 to 12 the QI and the flows coming deposits and forces the sum to be equal to 0. It is, on the one hand, the condition that arises when we apply the compatibility condition that we have studied, but, on the other hand, it is also the condition that, from an engineering and physical point of view, must hold, because the water neither creates nor it is destroyed, and what goes in has to be equal to what comes out. If in some case we cut the network, for example, if we remove 4 pipes, as you have there in the graph, what it is going to occur is that as compatibility condition, instead of a single equation, we will get 3, which correspond that what comes in and what comes out, in each of the 3 parts, has to be equal to 0. This is interesting, because there is a correspondence between mathematical solutions, which are the 3 above, with the 3 physical solutions, which are the ones that we must get. Now, let's obtain the set of solutions of this system. As it is a complete linear system of equations, we know that the solution is an affine space, that will have a particular solution, and a linear space. The first thing that has to be determined is the dimension of the linear space. In this case, it consists of 4 basic vectors: 3, 2, 1, 5, how many? So, I can advance you that I have proved a theorem that says that the dimension of the linear space is the number of holes in the network. In this network, if you look the previous figures, you see that we have 4 holes and, therefore, the linear space will have 4 basic vectors. So, the solution to this problem is the one you have there. We have 15 unknowns, a column vector, which goes from x1 to x15, and 4 rows appear, and 4 vectors, which are the linear space part, and then a concrete vector appears, which is the particular solution, what it is really interesting. This is what we would get if we apply the methods that we have explained mathematically, that is, if we use the algorithm. However, it would be a rather long process, because you have to iterate several times, one per equation, and they are already a little more complex matrices for doing it by hand, but we do not need to do it. The wonderful thing is that we do not need to do that. I'm going to explain you how to get this solution without applying the algorithm. First, let's see how you can get the basic vectors. If you look there, you have the network that has 4 holes. What we are going to do is to take hole by hole, and put the water circulating around the hole, that is, we're going to get special solutions in which all the pipes that make up the hole, the 4 pipes, water circulates, and, in the rest, water does not circulate, that is, as if they were closed or the pipes were sealed and there was no water circulating there. So, circulating in the indicated direction, we can find out that some of the x coincide in direction and some do not, that is, that some will have a positive sign and some a negative one. Then, if we assume that there is a unit amount of circulating flow, we will get ones, and minus ones, ones when there is coincidence in directions, and minus ones when there is no. Since it is a rectangle that has 4 sides, 4 unknowns will appear. So, we identify the corresponding unknowns, which in this case are 1, 2, 3, and 4, that is, x1, x2, x3 and x4. x1 and x3 circulate in the opposite direction of the turn, so that they have a negative sign, and the other 2 have a positive sign and all they have modulus 1. In addition, all other flows are 0. So, that represents a basic vector of the linear space. The next basic element is that of the next hole, so that we follow the same process, we select a turn, assuming that a unit flow circulates, and identify the variables involved and their associated signs, and put ones, or minus ones where appropriate. In this case, you see that the 4th, the 5th, the 6th, and the 7th, are the variables and there are 2 of them having minus sign, and 2 having plus sign. This leads to the second basic vector. The same thing can be done with the 3rd and the 4th holes. So, it's very interesting to check that we can write those vectors without using the algorithm, because we know, first, that the solution is a linear space of dimension 4, and that those holes give rise to linearly independent vectors, obviously, because their unknowns do not coincide. We have used a part of mathematical knowledge, which tells us how the structure is, and a part of engineering knowledge, which tells us how we have to put the signs and what vectors are different from 0. Finally, we have the particular solution, the last one. How can it be obtained? It's very simple. We know the amount of water that has to be delivered to each of the nodes. Then, what we do is, we select a set of paths to deliver this flow amount from the deposits. First, we choose one of the consumption points and we select a set of paths allowing to deliver the required flow amount. If a single path exists, this is the most convenient. For example, if I have to send 5 units of water, and there is a deposit with this amount of water, the path goes from this deposit to the point, and all unknowns we find take positive or negative signs, depending on the path and the unknown directions. That's what we do. We repeat it for all consumption points, and then we add all flows for all points paths, and we get the particular solution. This is a particular way of carrying the water that we need, from the deposits to the points, and because in that column we can put any particular solution, you do not need a special one, the resulting one will be satisfactory. With this, we have already solved the problem without any algorithm. We have combined mathematical knowledge with engineering knowledge, which has allowed us to obtain the set of all solutions. Let's see, then, what happens when we put capacity limits. Suppose now that we give the previous solution, so, since ρ parameters appear, this means that they are real numbers that have no limit as to sign and value, therefore, they can be positive or negative and as large or as small as we like. Therefore, in this set of solutions, there are solutions that have unlimited flows, and we know that this does not correspond to the real case, because the pipes have a certain diameter and are limited, having a capacity limit. So, the mathematical model that we have used is a theoretical model, that gives us infinite solutions, but it gives us solutions that contradict the reality, that is, with such high great flows, that they have no sense, because they could not stand on the pipelines. Consequently, we have to put more constraints on our problem, so that it makes sense, and the limitations that must be included are capacity limits, for each pipeline. Each pipeline, depending on its diameter, must have a capacity limit when water circulates in one direction, and a limit when the water circulates in the opposite direction. Normally, they will coincide in absolute value. Therefore, we can add to our previous system, that was the matrix equation that we have there, the constraints listed below, which are double constraints, depending on the flow circulating in one or the reverse direction, that is, minus Ci less than or equal to Xi, less than or equal to Ci, where Ci is the capacity of pipe I. Then, we no longer have a system of equations, but a system of inequalities. If we complete the system, this is what we get. We get that system that you have there. This is the problem that we have to solve with capacity limits.